Swayam Prabha. Digital India. Educated India.
Now at quasi-steady state, we know that the biomass concentration is not changing with time. It was a variable and this is now at steady state, so no change, dx by dt is 0. However, the amount of biomass in a fed batch process will keep changing with time because the volume is changing. So let's see how does it change. So let's assume the total biomass as xt at any given time t, and we know at quasi steady state dx by dt is equals to 0. Now this x can be written as xt, which is the amount of cells in the numerator, divided by the volume at that time. Let's assume it is v. So now dx can be expanded as xt by v as given here. Now this differential xt by v has been further expanded because xt and v both are variables. So then it has been further expanded as v multiplied by dxt by dt minus xt times dv by dt and divided by v square. This is how the differential is done for the two variable xt by v, and we know that this is 0 for quasi steady state. So this corresponds to the numerator is also equals to 0. So therefore your dxt by dt will become equal to xt by v from the numerator here will become xt by v dv by dt. Now dv by dt can be replaced as f, and this is xt by v is some concentration. Now assuming, as I said earlier, the purpose of the batch is to maximum cell concentration in the fed batch process. So let's assume it to be xm, which will be what then? At constant yield of the biomass. Let's assume yx by s, which is theoretical maxima. So in terms of that, we can write it as yx by s into s naught. This can be the maximum biomass concentration achieved, and s naught was the initial substrate. So this means s is nearly equal to 0, which is quasi steady state. As the substrate is coming in, it is getting consumed. So there is no net substrate. Then only you can assume maximum biomass production. So your S residual is nearly equal to 0 for this maximum biomass possible. So now this equation can be written in the form of yx by s, s naught into f. So now if we integrate xt, which was dxt by dt. So now with the limits of xt naught and xt, so xt naught is the initial amount of biomass present, s naught is the feed substrate concentration, f is the constant feed flow rate. So then this becomes a function of time with f yx by s, s naught and xt naught known. Yx by s into s naught, xt naught would be what? xm into v naught plus xm ft. So this xm into v naught was xt naught, which was the initial amount of biomass, where at the initial point where the substrate concentration was S naught, volume was V naught. So, the cell concentration was x T naught by multiplied by V naught. We will end up in the same scenario if we do a balance for the rate limiting substrate. Let us see it here. This is the rate of accumulation of the substrate at any time t, which is equal to the inlet substrate concentration, the rate at which the substrate is coming inside the reactor, and the rate at which the substrate is getting utilized. So, this is a substrate balance equation. St is the amount of substrate at time t, xt was the amount of biomass at time t, and S naught is the substrate concentration, and F is the volumetric flow rate. So, at quasi steady state, all the substrate is getting consumed. So, there is no significant level of substrate which can get accumulated. So, then in that case your Fs naught, so this goes to 0 and your Fs naught will become equal to mu xt by yx by s. So, if Fs naught is equals to mu xt by yx by s, then dxt by dt can be written as xt by v dv by dt. So, we are multiplying and dividing. So, then this becomes xm into f, which is f multiplied by xm was yx by s multiplied by s naught. So, now this equation xt is equals to xt naught plus yx by s naught ft, this demonstrates that once the quasi steady state has reached, this is how the biomass, although the biomass concentration is not going to change with time inside the reactor, but the amount of biomass with time is going to change inside the reactor as a function given here, where xt naught is the start during the once the quasi steady state has reached. So, at this point, once the quasi steady state has reached, the biomass, assuming it is your maximum biomass concentration, and then we continue to operate the system for the maximum biomass concentration all the time, so that it does not change with time at steady state. So, your xt naught is your volume, starting volume at quasi steady state multiplied by the maximum biomass concentration, which is yx by s into s naught. So, this is the initial amount of biomass once the quasi steady state has reached, and now with time at quasi steady state, this is how xm multiplied by ft, this is how your xt is going to change with time. Now, let us do a substrate balance. So, if we do a substrate balance, this is the rate at which the substrate is getting accumulated inside the reactor. This is the rate at which the substrate is coming inside the reactor, and this is the rate at which the substrate is getting utilized inside the reactor. At quasi steady state, the amount of substrate coming inside the reactor is instantly getting utilized, and there is no net substrate getting accumulated inside the reactor. Hence, your dst by dt can be assumed as 0. Whatever substrate is coming inside is getting consumed. So, there is no more accumulation of substrate. Hence, your Fs naught becomes equal to the term mu xt by yx by s as shown above here. Now, let us formulate how the product concentration is going to change in a fed batch process at quasi steady state. Now, the total product concentration or the amount of total product would be, let us assume PT, the product concentration is P. So, the amount can be obtained by multiplying P times V. V is the volume at time t. Now, the specific rate of product formation for most secondary metabolite is said to be constant. The amount of product formed cell or biomass per time. The amount, the rate at which the product is forming is equal to specific product rate multiplied by the amount of biomass at that time. This is what QP stands for. So, therefore, if in place of xt we expand from the previous derivation, we can write, being a quasi steady state, it will be a function of time xm and f, assuming that the fed batch process is running at its maximum biomass concentration at quasi steady state. Now, with the limits that at the beginning of the quasi steady state, the amount of product is PT naught, and this beginning of the quasi steady state, the time is assumed to be 0. If we integrate now this equation and put the limits, it will become PT is equal to PT naught plus, so with respect to t, the t has been taken common. Let us do this for clarity. So, the equation was dpt by dt is equal to qp times xt. So, if we integrate and put the limits, pt naught dpt is equals to, this is specific product formation rate which I said, so we can assume that, and in place of xt it has been expanded as V naught times ft multiplied by xm, and the limits as t naught to t, and this t naught is 0. So, here this will become, from here we can write it as pt minus pt naught is equal to qp. So, this xm is brought near to qp, and this becomes t square by 2. So, the t, and this was V naught into t, so the t has also been taken out common. So, now I hope you can understand how we have reached to this equation. Now, further simplifying it, rather than keeping in terms of the amount of product, we will reconvert it into the concentrations, because this is what we are measuring inside the reactor. So, in terms of product concentration, this will become equal to P is equals to, so what we will do, we will divide it throughout with a volume V. So, this now becomes equal to P, which we may call as, rather than saying it as PT, because then this becomes amount. So, we will call it as P now, the concentration at time t, and this goes to the right hand side. So, PT can be written as initial product concentration multiplied by the initial volume, which is known, divided by the V plus QP XM V naught by V. So, V has been taken inside the brackets, and this F by V then becomes D by 2 multiplied by. Now that you have understood this equation, from this itself, as I said, we will divide the entire equation by V to make it as a function of product concentration. So, this becomes product concentration at time t, and PT naught further can be written in terms of product concentration as P naught V naught as given here, divided by V, because the entire equation has been divided by V, and this V has been brought inside the brackets. So, the F by V which came here we know D is equals to F by V. So, F by V has been replaced as D here and rest is kept as it is. So, we end up in this equation. Now, further expansion, V we know is a function of time for a constant feed flow rate system, assuming the constant flow rate as F. So, it has been further written as V naught plus F T here throughout the equation. So, now we know how the product concentration will change with time for a quasi steady state fed batch process.